right, so I need to do a couple more lecture segments. For the people in the class, you can think of it as optional. I hope it would be useful for people who are trying to learn about multidimensional spectroscopy, which is one of the sort of, let's say, more frontier aspects of spectroscopy in physics and chemistry. It is established in NMR, but the thinking that we use in optical domain is quite a bit different from what people use in NMR, even though a lot of the techniques are very analogous. What I'm going to do is I'm going to go back to the response functions and take them one by one and notice that there's a way of representing the various contributions to the response function graphically. And once we have that graphical representation, it can be much, much faster to interpret 2D spectra, for example. But not just 2D spectra, also things like second harmonic generation or some frequency generation or any other kinds of combinations of experiments that you can make where you add more field interactions. Now you might say, why would anyone want to do that? Okay, and I'll tell you right now, the punchline is thinking back to the Kubo model. Now, of course, the Kubo model is like a model, right? It's still a sort of a phenomenological model. You assume that there's some frequency fluctuations. But I think that's pretty physically motivated. It's not too hard to imagine that frequencies would be fluctuated because of an environment. And so remember that one of the key, if not the key, ingredient of that is this frequency fluctuation correlation function. And as I said then, it's obviously super important for calculating the line shape. It's the key ingredient. But it's not something that you can measure the line shape and invert it to figure out what this is. There's an infinite number of frequency correlation functions that'll essentially give you the same or indistinguishable absorption spectra. So it's really not possible to do this inversion. The question is, can you measure this directly? Okay, and the answer is more or less yes. There are some caveats in terms of like some limits need to be applied and so on. But generally speaking, you can measure this. Okay, which means that you can detect the time scale on which a frequency loses its memory of the initial excitation. Now, why might this be interesting? One reason it might be interesting is because you might want to study molecules at equilibrium. The classic example I gave for you of that was a hydrogen bond. Right? The idea is that you have a hydrogen bond here between two oxygen atoms. The OH stretch frequency will be different depending on the oxygen-oxygen distance. So what you would like to know is if you excited a molecule when it, say, had a short hydrogen bond, you might ask how long does it take to either have a long hydrogen bond or just become randomized amongst all the other possible configurations. Obviously, you don't literally excite one molecule, although maybe in the future there'll be techniques that allow us to do that. So instead, what we do is we look at the correlation function. This correlation function could be exponential, but it doesn't have to be. There could be multiple timescales. Let's just say for fun that it's exponential. All right, well, then you get a time scale, some time constant, 1 over e. This time here will be 1 over e time. All right, and then you could say, see what happens if you make some change to the system. Like if it's just water, then you might change the temperature of the water and see, oh, how does the time scale of this frequency correlation decay change if I change the temperature of the water, right? Another thing you could do is say, well, is there any water? No, of course not. There's no water anywhere. There's no pure water. Even the purest water in the world, which is made in the semiconductor industry to clean the silicon, still has some finite concentration of contaminants in there. And in real life, like in your body and in the ocean and lakes and in ponds or in the rain, there's no such thing as pure water. So water itself, pure water, is a construct. What's really important in our real lives is having something in the water. So now you can add some salt, you can add some other kind of solute, you can add a protein, you can add a membrane, you can add a lot of things. And then you can measure what happens to the dynamics that you probe with the OH stretch as a function of changing all of these things. So one example that people have done that has been pretty productive has been to, for example, cloister the water, keep it located in a small region. And you can do that if you can make something like a little pool of water. And one way to do that is to use what's called a reverse micelle. So in a reverse micelle, you have these surfactant molecules, which are amphiphilic. So they have a polar head group and a nonpolar chain, like a hydrophilic end and a hydrophobic end. And you simply mix together water, the surfactant, and an organic, solvent. This is our organic solvent, like a alkane or something like that. And then we have water inside. And the idea is some of that water will interact with the head groups, and some of it will be sort of located in the middle. And the idea is, could you detect the heterogeneity of the dynamics of the water, knowing that they're going to have some sort of structural distribution like this? And sure enough, you can do that. So Mike Fayer's group has done quite a bit of this, work with Nancy Levenger, to study hydration dynamics inside micelles, reverse micelles, by taking advantage of the fact that there's pretty much a slowing down that occurs at the interface, and then bulk-like water in the middle, so that you can actually see the time scales change as you change the size of the micelle, which you can do by simply changing the concentration of the surfactant or the amount of water to alkane that you have. Okay, so you can change the size of the micelle. They're not perfectly round like this, of course, and that can change the size. My group studied it in a slightly different way. We made reverse micelles. We added thiocyanate. Sodium thiocyanate dissociates into water, and the thiocyanate anion will, it turns out, attach very sort of vehemently, much more than we thought, vehemently to the polar head groups. It's really hard to get rid of it. We added iodide, we added chloride, couldn't get rid of it. So we used 2D IR, and we also used NMR spectroscopy, and we used basically if you wanted to sound fancy, we used chemical shift perturbation. So you look at an NMR spectrum of the micelle in the water, and you add the ion, and you see, does the chemical shift change? And you look where in the spectrum it does, and then since you know how to assign the spins, the transitions, you can say which part of the micelle surfactant molecules is altered by this. So these are ways that you can use dynamics to measure structural heterogeneity of the composite material, as well as, of course, something about the dynamics in there. And the observable is this time scale for this decay of the correlation function. We call this effect, the decay of the correlation, we call that spectral diffusion. We call it spectral diffusion because the way to think about this is that there's some spectrum, right? Some inhomogeneously brought in spectrum, whatever the amplitude, fine. It's a function of frequency. So thinking of the Kubo model, closer to the inhomogeneous range than, let's say, purely homogeneous. What that means is you can think of the frequency fluctuations as being not instantaneously fast. So there might be some time scale where something samples and stays for a little while in a particular, let's say, sub-configuration here, sub-configuration here, sub-configuration here, right? And so the idea is you just have some random sampling of all the different configurations, and that's going to give you these sort of line shape that's underneath this. There are these sub-ensembles that correspond, for example, maybe to that one or whatever. Obviously, if this is high frequency, it should correspond to that one, and this is low frequency, and so on. Now, we can't measure this correlation. We can't measure the trajectory. You can do simulations where you might be able to get some information about this. But we can measure its correlation function, and that's what is the whole point of this. Now, what's the problem? The problem is, what if we have multiple timescales in the correlation function? Let's imagine you do an experiment and you find out it goes like this, right? Which is maybe not fittable with a single exponential, and maybe it's not even fittable with 5 exponentials. We've done experiments like this too. Incidentally, so has the Fair group, more than we have, looking at glass-forming liquids. in a glass-forming liquid, what happens is you can have a dramatic slowdown in the dynamics near the glass transition. Just think about how if you take honey and you cool it down, it gets really, really rigid. If you warm it up, it gets very runny. Right? So it has a very strong temperature dependence to its viscosity. Most things have a temperature-dependent viscosity, but some things become glass-like, sort of like this, although this might be a crystal. And we know thermodynamically the lowest energy state is a crystal, but sometimes you can't get to that crystal state. You need a barrier, you need some activation. And in a glass, that barrier is basically insurmountable. You can never achieve the crystal. What that gives us is a material that seems to be kind of fluid a little bit, but the flowing rate is very, very slow. So now you might ask this the question, if I could look at a region of if I could look at a molecule that had a correlation function like this, would each molecule have the same correlation function? So that I have only one kind of homogeneous dynamics? Or is it really that I have multiple different kinds of correlation functions? So I might have like the probability of having a rate constant or a time constant for spectral diffusion that's still exponential, but I have a distribution of them, let's say P of K. So if that's the case, you have heterogeneous dynamics. Well, it turns out you can't separate this scenario from the scenario where every molecule has the same kind of dynamics with only a single dimensional correlation function. To separate this out, you need to have a higher dimensional correlation function. You need to have two different time periods where you look at the frequency correlation in one compared to the frequency correlation in another. Right? Well, how do you do that? You can do that experimentally. You just need to have an additional time period in your experiment. So whereas a 2D experiment has three time periods in a signal, T1 and T2, which we can control with our laser, and then we detect in the spectral domain for T3, the waiting time, the time where we have the correlation between excitation and detection, is this one here. This gives us a one-dimensional picture of the dynamics. What if we have a scenario where there's different species? So for example, in the micelle case, the picture that the Feyer group has put forward is that you have a bulk-like center and an interfacial slowed down interface. That would imply two. Right? That's a pretty simple way to do it. And you can fit this all with two exponentials. That's pretty cool that they can do that. All right. What about if you had a continuous variation, or if each molecule had different timescales? Well, you wouldn't be able to tell. You could probably still fit it though. So the way you do it experimentally is you add more pulses. So you have two population or two waiting times. Right? This is a coherence time, so we'll call that T1. This is the first waiting time, T2. Then you have another coherence time and another population time, and then the signal. So now you have three inputs and one field, that's 4-wave mixing. Here you have 5 input and 1 field, so that's 6-wave mixing. And this is a 3-dimensional experiment because you have frequency during this time, frequency during this time, well, that's another one, and frequency during this time. Here you have frequency during this time and frequency during this time. Right? Whenever it's in a coherence, that's when you have frequency. A high frequency, a coherence between a ground and excited state. Okay, so what this means is you can correlate the spectral diffusion in this period with the spectral diffusion in that period. All right, so what you can see is that the more pulses and more fields you interact with, the more information you can get, the more of the approximations, the Gaussian approximation. You can get past the Gaussian approximation with this. But you can't get it past with this. You could not tell if it's Gaussian or not with this experiment with only one population period. So the question is, well, what do you do if you want to design experiments for the future, not just to understand all the stuff that old people like me have already done? You want to do you're the next generation. What are you going to do? Well, lasers are easier to get now. There's so many more different kinds of lasers that you can get. The lasers aren't the problem. You can make mind-bogglingly intense infrared pulses, extremely broadband visible pulses. It's pushing into the UV. It's more and more common to do X-ray experiments, obviously not in your own lab, but at facilities. There's going to be the ability to do much more complicated pulse sequences and manipulations of coherences and populations in the future than there ever were than there are right now. So just understanding what we can do now is not enough. You need to be able to think in the future what's next possible. So that means usually adding more fields. They don't have to be the same frequency. They could be visible for these and then infrared for that, or ultraviolet and infrared, or ultraviolet and visible, and so on. So you can mix and match frequencies. We do this in the Lumos lab right now. So that's what we do now. What about 10 years from now? If I think about 10 years ago, a lot of things that we do now would have seemed insane 10 years ago. All right, so what we can do is we can add more pulses in. We can add more fields. Now, do we need to do 1,000 equations every single time we add more fields? If we do, then we're really in trouble. Turns out you don't need to. Every new experiment, it might have a complex interpretation from the point of view of the chemistry. I agree. It's not always so easy to figure out what these experiments are useful for. I honestly say that. But I can at least tell you why there's a signal and what the peaks in the spectrum will mean. And this is how you do it. And it's a really cool method of listing and graphically these very complicated, or I don't know, somewhat opaque expressions that you get when you just write down the response functions. Let's remind ourselves from the very beginning, first order, S1, has one time variable, which you could call T1 or T, it doesn't matter. So we have I over H bar, we have the Heaviside function, and then we got these two J terms, like J of T and J star. Don't forget this minus sign. The minus sign is important. Where does the minus sign come from? Of course, it comes from all those commutators. That minus sign, those commutators are going to be the reason why some signals in our experiment are positive in amplitude and some are negative in amplitude. All right. So then remember what the J's were. J was whatever your interaction is, evaluated at T. And then J star is the swapping. All right, so you got that. Now, what about, so what we're going to do now is we're going to remind ourselves sort of what does this mean? How do you calculate this expectation value? And the way you calculate this expectation value is that we need to do the trace, right? Doing the trace is basically how we get an expectation value. So what we're going to do here is we're going to write down this in terms of the trace. And now what we're also going to do is we're going to expand the V's. Right? I'll do this first sort of slowly with the linear one, and then I'll do a couple examples from the nonlinear examples. All right, so what do we mean when we say V of T? We mean V of T, we mean whatever the operator is for V. So let's just simplify for now that V goes to mu, right? The dipole operator, which is of course what we expected to be for a spectroscopy. And then that's it. I'm just leave it as mu. Remember the field part is already extracted. If we're looking at the S part of the response function, the polarization will be the convolution of this response function with the fields. The fields are out. So the minus part is out, right? The minus sign is already out. That's why there's no minus sign here. And then the field part is already out as well. So that leaves us just with mu here. And mu is the dipole moment operator. It doesn't change. The reason why this has a time dependence is because we were in the interaction picture. So we put back in literally what the interaction picture is. So U naught dagger T, mu, U naught T. And then we have mu again at 0. We don't need to put anything on the sides of 0 because e to the minus I0 is just 0. All right, and then rho EQ. So what you'll notice here is that you have a bunch of operators, right, all multiplying by each other. But remember, it's inside a trace. This is super, super important. Because it's inside a trace, remember the number one rule about traces is that they have this invariance to cyclic permutations. It's a pretty amazing property of that. It's not like they all commute, but you can go around in a circle. All right? So even though there's more than 3 operators here, I could always put an I one place. So if I only have 2, you can always stick I somewhere. Right? And I can always lump together some operators and call that like B, right? So just for the heck of it, you know, if I wanted to, I could call that an operator. I can call this an operator and this one. So I could call this A, B, C. So now I can turn around. So I know that this trace is also equal to moving this over here. So I have mu u naught t mu rho eq u naught t. Right? That's just putting BCA. Now what do you see? It looks like not much has happened here. But actually, it is pretty incredible what has happened here. Let's interpret this. So we're going to interpret this way. We have our initial starting state here. We operate from the left with mu. Now remember, we did this example a long time ago with two-level systems. We know what happens when you operate on the left side with mu. You interact with the ket side of the density operator. So this is going to change. Let's say we know that rho eq is in a population because it's in equilibrium. Let's say just for the simplicity, it's in the ground state. Then what we're going to do is we're going to make a coherence with one of the excited states that we're resonant with. Okay, and that's what's going to happen after this. So I'm going to call the effect of doing mu on this. I'm going to call it mu, and I'm going to remind ourselves that we're doing it from the left. So I'm going to call it mu sub L. All right, this just means the density operator you get when you operate with mu from the left. All right, it's another density operator. Nothing happens yet. It just, we shift, for example, population from the ground state. And this is the, remember, this is the ground state, for example. This is GE. And then this, I'm writing down our basis in a kind of two-level basis. Here we have EE. And right, I'm just not able to fit it on here. And this one here is EG. Right? So going on the left, we're going to go like this. So we're in a coherence on the left side. Now what we're going to do, so we're going to call that rho mu sub L. Now what we do is we notice, what do we have? We have, this is the, remember, this is the time evolution of the density operator. So this says, take that density that you got by putting it into a coherence and evolve it in time using the time evolution operator for the field-free case. So this whole thing here becomes rho mu L, the density operator we got by having just converted it to a coherence, but now it's at time t. Okay? And then the final thing is the mu rho trace. That's the expectation value of mu for the system that has evolved the way we said it should. All right? So this is a way of understanding how to track the pathway through Liouville space and to get ultimately this expectation value of mu, which is what gives us our response function. Now notice the trick. The trick is very important. The trick is this written out like this, it's kind of not clear what goes on, right? You could sort of say, well, I have the density operator, then I operate it with mu, then I evolve without mu, then I operate with mu again, then this happens. This is confusing. Why this? This looks like I'm going back. So when you move it around, because the trace doesn't care, it makes much more sense what's going on. We have a density operator, we operate with from the left, we evolve it forward in time with the time evolution operator, and then we have the final mu that comes from just computing the trace. So I had to put it in the right order. I had to put it in order where the time goes from sort of from left to right. Now what we're going to do is we're going to see there's going to be some of those response function terms that are weird, right? Because they're like out of order. So how do I put those together in the right way? So first thing I'm going to do is show you how to put them in the right order, doing tricks like this by just rotating around in the trace. And then I'm going to show you how you can associate with operation from the left versus operation from the right and link that back to the specific signal that you're trying to measure in the lab and figure out how do we list all of the pathways and interpret them. Okay, let me just, obviously this is the easy one. It was already sort of written in the correct order. Let's look at this one, which looks really weird. It's like saying the density, I start in the ground state or I start in my equilibrium and I do something with the dipole at time t, but then I come back and do something at the zero. It's like, what is that all about? That doesn't make any sense. So you'll see you can do a trick just like the one I showed you. So let's look at this the J star term. Now, of course, we already have this one, so we could just take the star of it. But let's see how to think about it first. So we're going to have trace mu. I'm already making the switch from V to mu, and I'm already going to make the switch from interaction picture to regular. All right, so we have mu, then we have the way you do V normally. So that's U naught mu U naught of T, and then rho EQ. Right? So what are we going to do now? We're going to move it around as we did before. Okay, and so what we can do is we can move both of these over here, right? Because I can call this operator A, B, C. This is equal to trace mu U naught of T rho EQ mu U naught dagger. So what's different now? What's different now is mu is operating from the right on rho. Okay, well, we know what happens when mu operates on the right. It's going to go to this other coherence. We worked this out like 3 or 4 weeks ago. All right, and so now I'm going to call that rho mu from the right. And now everything else is exactly the same as this. We have the time evolution transformation, right, which evolves the density operator forward in time. So now this becomes then rho mu right at time t. We take this as the state of our system. We compute the dipole moment expectation value, which is to do trace rho mu or trace mu rho. And we're done. All right, and so then we see that we can list the pathways by this trick of organizing all the interactions in such a way that we can have the correct ordering, even if the ordering looks ridiculous. All right, and so this just shows you that the two contributions to your linear absorption spectrum are an interaction from the left plus an interaction from the right. And of course, they're not different from each other. They're related by a complex conjugate. In practice, because we know that there's always going to be this symmetry, a set of response function subcomponents that are equal to the complex conjugates of another, we only need to actually ever evaluate half of them. So either this one or this one is fine. All right, so the next thing I'm going to do as an example is with the second order, to show you how you can do it with second order. And just so you can see how that works. I'm not going to do a lot of the terms. I'm just going to do one. It's a little bit, it's the same thing over and over again. And then we're going to go to talking about how to link the response functions to the experiments that you do, and then diagrammatically work out what are all the pathways.